Hello, I am Vasileios Baltatzis from Imperial College London, and I will present to you our work titled Neural Sign Actors, a diffusion model for 3D sign language production from text. Sign language is the primary form of communication for more than 70 million deaf and hard of hearing people. Sign language can be broken down to the manual modality, which involves hand articulation and motion, and the non-manual modality, which involves arm movement and facial expressions. Whilst it is possible to convey some meaning using just hand articulations, expressiveness is limited since non-manual elements often convey emotions. Deep learning methods have been proposed to bridge the domain gap between sign and spoken languages. Most methods focus on sign language recognition, which includes the translation of a specific sign to its corresponding meaning, as well as sign language translation, which extends sign language recognition to the translation of a sign sequence to its spoken word equivalent. However, sign language production remains the most challenging and least explored task. The main challenges that have hindered the development of effective sign language production methods revolve around the lack of large-scale datasets that pair text with 3D sign avatars. Most of the existing methods focus on 2D skeletons, and their generations suffer from limited expressiveness in hand and body motion. To deal with these shortcomings, our work focuses on two main directions: the generation of a dataset that pairs text with 3D avatars, and the development of a generative framework that, given a text sequence, produces 3D avatars. Before we get to the main part of the paper, let's discuss first some prerequisites. The primary dataset that is utilized in this work is the How to Sign dataset, which is a large-scale dataset that contains more than 30,000 videos of sign language paired with a corresponding text sentence. To represent signs in 3D, we leverage SMPL-X, which is a 3D human body model that is parameterized by 179 parameters involving pose, shape, and expression parameters. Now let's move on to how we create the 3D sign language dataset. The fitting pipeline receives as input the videos from the How to Sign dataset. The outcome of this pipeline are sequences of 3D SMPL-X representations that correspond to the frames of the input video. To do so, we initialize our fitting optimization using the SMPL-X pose and shape parameters acquired from OS/X for each frame. Hand poses constitute the pivotal component in conveying sign language, and therefore we adopt an optimization procedure to enhance the precision of hand poses and rectify any potential misalignments by leveraging body and hand joints detected from the MediaPipe framework. This is performed through a reconstruction loss between the initialized joints and the joints predicted by MediaPipe. To constrain the optimization to plausible human and hand poses, we propose a simple but intuitive approach using principal component analysis to model the subspace of anatomically feasible poses. Finally, to tackle the presence of jittering and potential spatiotemporal noise in the joint detections, we deploy a temporal coherence loss between consecutive frames. Accurate 3D annotations are required to train a potent SLP model. To assess the fitting quality, we deploy the proposed pipeline on the Signify mockup dataset that contains ground truth annotations and report the mean per vertex error. Additionally, we qualitatively confirm that the powerful prior model that guides the fitting optimization leads our method to valid poses and articulation. Here you can see example fittings from the How to Sign dataset. Now that we have our dataset in place, we can describe the primary architecture of this work, which is a diffusion-based generative model that generates motion sequences conditioned on text transcripts. Similar to traditional diffusion architectures, our method is composed of the deterministic forward diffusion process that gradually adds noise to the input distribution and the reverse denoising model that predicts the noise introduced by the forward process at each time step. The proposed denoising module can be divided into three main components: the anatomically informed pose and expression encoders, the text encoder, and the autoregressive decoder. For the anatomically informed encoder, we combine a graph neural network with a pose embedding layer, which allows us to enforce the joint poses are affected by each joint's neighbors according to the SMPL-X kinematic tree. To encode text descriptions, we utilize CLIP as a powerful sentence encoder that is able to generalize to arbitrary text prompts. Finally, considering that motion can be conceptualized as a sequence of poses where each pose is contingent upon its predecessor, we constructed our motion generative network utilizing an autoregressive model. We quantitatively evaluate the generation quality of the proposed and the baseline methods under a set of metrics. The first two were mean per vertex position error and mean per joint position error. Given that the motions generated from the proposed and baseline methods may not be correctly aligned with the ground truth annotations, we use dynamic time warping to measure the similarity between the generated and the original sign sequences. To evaluate the quality of the generated poses, we measured the FID score between the generated and the ground truth poses. Finally, we trained a transformer-based back translation network to map pose sequences back to text. All reported metrics indicate that our method considerably outperforms the competing approaches. Although evaluation metrics can provide insights into a model's performance, the most critical benchmark lies in the perceptual evaluation from deaf and hard of hearing individuals. We assess the realism of the generated signs by designing a user study where 15 ASL fluent subjects evaluated the generated signs. We divided the perceptual study into two parts to determine first how aligned the generated signs are with respect to the text transcripts, and second, the fidelity and readability of the proposed generations. For the first part of the user study, we presented 15 different generated signs from both the proposed and baseline methods alongside the ground truth video and its corresponding fitting. Participants were asked to assign a value between 1 and 10, rating the alignment of each method with the corresponding text transcript. As expected, the ground truth videos achieved the best average score of 8.7, while the fittings achieved slightly less with 8.1, which quantifies the high quality of the generated annotations. The proposed method achieves a respectable average score of 5.8, whereas the competing methods failed to achieve reasonable results. The second part of the perceptual study aimed to assess the fidelity of the generated signs. Each participant was shown 15 rendered videos with signs generated by the proposed method and was asked to rank 4 candidates' text translations from most likely to least likely translation. Measuring the cumulative accuracy, the generated signs attained a top 1 accuracy of 40% and a top 2 accuracy of 80%, affirming the realism and the fidelity of the generated signs. Here you can see some examples of generated sign sequences. It is important to note that the only input for the model is the text sequence. The original video is only provided here for reference. Neural 3D sign language production is an important challenge that aims to aid the deaf and hard of hearing community and can effectively increase their inclusion in any social environment. In this work, we made a step towards high-fidelity 3D SLP by deriving a large-scale 3D dataset to train a text-conditioned diffusion-based model. We initially introduced a precise 3D sign language reconstruction pipeline that outperforms previous sign language reconstruction methods. Then, we trained a motion generation model using an autoregressive diffusion model. The core of our method is founded on a novel, anatomically inspired graph neural network that learns the pose distribution and enables high-detailed articulations. Extensive experiments on sign language generation tasks, including a perceptual study with ASL fluent subjects, demonstrate the superiority of the proposed method compared to the previous approaches. Future work involves improvements on the SLP pipeline and exploring additional databases that will allow the training of more robust and generalizable models. Thank you very much for your attention. Looking forward to seeing you at our poster at CVPR.